I was going to talk about a couple things that we didn't quite get to in 2.1. First thing was a theorem that I had planned to do a short proof of, but we ran out of time. And it says the sum, and it should say or difference, not of. The sum or difference of two differentiable functions is differentiable. So what we'll do is we'll suppose f and g are differentiable at some point c. And what we'll do is we will use our definition of limit, our definition of derivative using the limit. So here's the statement of it. So f plus g prime of c means the derivative of f evaluated at c plus the derivative g evaluated at c, or f plus g derivative of c. So we will go ahead and see if this limit exists. So our function is f plus g. So we'll take the limit as h goes to 0, f of c plus h plus g of c plus h minus f of c plus g of c. And then we'll go ahead and break that up into f of c plus h minus f of c over h plus g of c plus h minus g of c all over h. And then we'll use a theorem that we had earlier in chapter 1, which says if I know the limit of this first function and I know the limit of this second function, then if I take those two functions and I take their limit, then the limit of the functions, the limit of the sum of the functions is the sum of the limits. So that just becomes f prime of c plus g prime of c. And that's it for that one. Real short proof. What else did we want to look at? We had an example that we didn't quite get to. So it says the annual inventory cost C for a certain manufacturer is C equals 1,008,000 over Q plus 6.5Q, where Q is order size to be replenished. And they would like us to find the rate of change from 350 to 351 and and compare that to the instantaneous rate of change at 350. So we're going to see that what we're really doing here is we're finding a slope of a secant line connecting 350 to 351 and whatever their corresponding y values are, so connecting those 2 points, and then we're going to find the slope of the tangent line at 350, and we're going to see how close they are, and be sort of like a linear approximation. Sometimes it might be easier to use the slope of the derivative, and then the derivative will give us a slope, and then we can use a line, and that line will, in a small scale, will approximate what the graph is doing, and lines are easier to use than some functions. So first thing we'll do is find the rate of change. So we're just going to find the slope between the 2 points. And so C of 350 minus C of 351. So what we're going to do is we're going to plug 350 into the C formula for Q, and then subtract from it 351 in the C formula, and then 350 minus 351. So all that is finding the slope. So what we get is negative 1.9051, and that's your slope of the secant line. Now if I want to find the instantaneous rate of change, that requires calculus, and that requires us to take the derivative. So we're going to write the C function in a slightly more friendly mode here, and I realize I don't want a C here, I want a Q, so we're going to change this into a Q. So Q to the minus 1 is the same thing as Q in the denominator. So we will use the power rule. So we're going to bring that negative 1 down. So negative 1 times the 1,008,000 will give us negative 1,000. Jeez, I can't talk. Negative 1,008,000. And I did it again here. I guess I really liked C when I was doing this problem. So this should be a Q. Sorry about that. Q to the minus 2. And then the Q on the 6.3 is going to go away when we take the derivative. So it'll just be 6.3. And we don't need a Q there. Okay. And now what we'll do is we'll evaluate it at 350. And if we plug those numbers in, we get negative 1,008,000 over 350 squared. Remember, the Q to the minus 2 is the same thing as Q squared in the denominator. And we're plugging in 350. And then 6 plus 6.3. Remember, the Q went away when we took the derivative. So crunching those numbers, we get negative 1.9283. And you can see the slope of the tangent line, which is what we did in yellow here, is real close to the slope of the secant line. So the average rate of change is approximated by the instantaneous rate of change. And maybe we wanted to find the actual line there. And first, in the small scale, we could use that line to do a fairly good approximation of what the function's doing. Okay. And we had one other example that we didn't quite get to. And we had find K such that the line is tangent to the graph y equals x plus 4, where f of x is equal to k square root of x. So we want to find where that line is going to be tangent to this graph. So we need to find the k, though. So what we'll do is we'll mention that the slope of y equals x plus 4 is 1. And f of x is the same thing as k times x to the 1/2 power. It might be a little bit easier to take the derivative. So the 1/2 comes down, k, and then subtract 1 from the exponent. So we have k over 2 square root of x. Now the derivative function is going to give me a slope at a particular point. We don't know what point these two graphs are going to intersect, so the x plus 4 and the k square root of x, they're going to touch at some point. We don't know yet, but we have enough information here to kind of find that out. So I want to know, when is k over 2 square root of x? When is that going to equal 1? So 1 is going to equal k over 2 square root of x. So 2 square root of x is going to equal k. Now y is equal to f of x. Now why we're saying that is, where are these two functions equal to each other? When is x plus 4 intersecting f of x? So that's going to help us find the location of where those 2 points intersect. So we will go ahead and substitute in y was x plus 4. And f of x was k square root of x. Now we needed to do this other stuff so that we would have we'd have 2 equations and 2 unknowns, because I don't know what k is and I don't know what the x is. So the derivative helps set up one of the equations, and then where the 2 graphs intersect is going to give us the other one. So we're going to go ahead and substitute in for k 2 square root of x. Okay. And x has got to be greater than or equal to 0 in order for the square root function to be defined. X plus 4 is equal to 2 square root of x squared, which is just 2x. Subtract x from both sides, and we have x is 4. Okay, so x is 4. That's where they're going to intersect, at 4, comma 8. And we can use this function here, or this equation here, to find what the k is. So k is going to be equal to 2 square root of 4, which is also 4. So we found the k. That's what they wanted us. K has to be 4. Now I'm going to try to do a rough sketch for you. So there's your line, y equals 4, and then there's our square root function. And you can see that it's tangent at one particular point right there. So that's what we had to do. We had to find what the K was, and we also had to find where they were going to intersect so that we had this happen. You have a couple examples in your textbook that might have you do this. Now, I don't know if I can zoom in, but if we try to zoom in, I don't know if this is going to show up on YouTube, but if we're looking at this region right here, you can see that the line does a pretty good job of approximating the square root function. Also, you might have to blame the artist because the artist may not have been real great at drawing the picture, but you can kind of get the idea there that the line does a pretty good job of approximating the square root function at that particular point.